So I was a little bit
locomotives are
over ambitious with the questions, so we're not going to be able to go through all of them since it's like rotational, 1D, 2D, monuments, all of that. So we'll just go over a few of them, and I'll explain a lot of it. So first,
this one is like
part of what I want to do is I want to teach you guys the history of physics, how it's used in our everyday lives, and what kind of solutions we have for it. But I also want to explain, we all have all these formulas like that. So I want to show how we get those formulas because I think it's pretty cool, and you can see it's a little bit easier for you to memorize too and understand. So, I bet at this point you know the uniformly accelerated motion equations, right? Like delta x equals velocity initial t plus half at squared, like something like that. Can you see the screen, by the way?
Yeah.
Okay. So you know this at this point, but you're like, I mean, how do you get those formulas? Like, it just came out of nowhere. You're just told to memorize them, or you told that it's helpful or something. So I want to show it off. So, what's we know a velocity over time graph looks like this, right? That's a velocity over time graph. I don't know if I can make this bigger. Like, that's a velocity over time graph. That's simple enough. Let's say this is velocity initial, and this is velocity final. Let's say, so what is velocity over time? That's acceleration, right? So if the acceleration is constant, because kinematics, it assumes that the acceleration remains constant. So we have a constant line here, meaning a constant acceleration. So now we can divide this into blocks, because I think Nurstania showed you before. So you can break these into components to, like, here you have now a box, right? And you also have a triangle. So now you have a great understanding of what you're looking at. Now, what do we know what acceleration is, the formula acceleration? It's change in velocity over the change in time, right? So what is that? That's the velocity final minus velocity initial over t. So A equals velocity final minus velocity initial over t. I mean, if we want to solve for velocity final, we can move it, so we can do normal algebra. So it equals at, how is it? Velocity final minus velocity initial equals at. And then we can make it alone, so at plus velocity initial. Or you would normally see it as velocity final equals velocity initial plus acceleration time. If you remember, this is our one of our kinematic equations, and we only got it from just what? Acceleration. We just did normal acceleration formula. We simplified it out to make it a formula for us to find solutions easily. And remember, acceleration remains constant. So we have one, right? Does that make sense? Okay. If we want to find, what do we know that the area under the curve of a velocity graph? This would be what?
Displacement.
Yeah, displacement. So what is displacement? It's the area under the curve, or integral, whatever you want to call it. So if it's the area under the curve, what is the area of this box? It's just t times velocity initial, right? Because this is where velocity initial starts. So what do we know? If this is the displacement, then we know the area of this box, which is velocity initial t, right? Now what's the area of a triangle? It's half times base times height, right? We know that the base is t and the height is velocity final, right? So it's plus half, and we know that the height is velocity final minus velocity initial, because we have to consider this, right? So it'll be velocity final minus velocity initial t, because base times height times half. So Okay, this is similar. It almost looks like something we already know, but it's not perfect. Well, what else do we know? We know that AT, where is it? Velocity final minus velocity initial equals AT, right? Because we got it from acceleration originally from the original acceleration formula, and we got AT equals velocity minus velocity initial, right? So what can we do? If this equals this, then we can just put it in, right? So delta x equals velocity initial t plus half AT times t. So what does that become? Velocity initial t plus half AT squared. So there we go. We got another one. Another uniformly accelerated motion equation. Right? Doesn't that seem make a little bit more sense, right? When we get these equations. So what's another one? We got velocity average. What's that? That's what, delta x over delta t, right? So how do we get delta x alone, right? How do we get delta x alone?
Multiply the denominator to the x.
Yeah, exactly. So delta x equals velocity average times delta t, or t, whatever you want to call it. So what do we know that velocity average? We know that the velocity average is delta x over t, right? So hold on. So velocity average equals velocity initial plus half AT squared over t. Because we know, if we look back at here, right, delta x over delta t, what do we know delta x is? Velocity initial t plus half AT squared, right? And what's t? T is just t, right? So if we simplify that, what do we get? We get what? Velocity initial, that should have been t there. Velocity initial plus half AT. So what else can we do? That's velocity average. So we know that velocity average over t can equal to 2 velocity initial plus AT over 2. Because what do we know? You'd be like, well, how do we get here from here, right? That's a bit confusing. Like, where did you suddenly get a 2 from? That doesn't make sense. Well, what's 2 over 2? That's just velocity initial. And what's 1 over 2 for AT? It would be just half, right? So we just made it a little bit more difficult than it has to be. So so far it makes sense. So, but what can we do with velocity initial? What is velocity 2 velocity initial equal? It's velocity initial plus velocity initial, right? So we can simplify this to velocity initial plus AT over 2. Now that makes sense. So we can simplify it as, because we know what? Velocity final equals velocity initial plus AT, right? So if velocity initial plus AT equals velocity final, what does this become? Velocity initial plus, we know this is velocity final, so it becomes velocity initial plus velocity final over 2. So that might seem familiar. It's not a uniformly accelerated motion equation, but it's the start of something, right? Well, what do we know so if we come back here, we said that delta x is the velocity average times t. So if we know velocity average now, right, we can plug it in. So delta x equals velocity initial plus velocity final over 2t. So that becomes what? Another uniformly accelerated motion equation. Let's see. So now we can do this. What do we know what t is? Acceleration equals delta v t, right? Because it's the same thing as delta x, but the next step up for derivative-wise. So it's the same thing. So what if we want to get t alone? We do the same thing, right? So t equals. Oh, sorry, not over t. It should be acceleration equals delta v over delta t, right? Sorry, I made a mistake there. So that's delta v over delta t. So if we want to get t by itself, we just do the normal thing. So t equals delta v over a, which is velocity final minus velocity initial over a. So if we come back here, we know what t equals, right? So if we do delta x equals velocity initial plus velocity final over 2, and we multiply this here, velocity final minus velocity initial over a, we can simplify this out because we know that delta x 2a equals what? Velocity final squared minus velocity initial squared. So if we want to simplify this, if we want to simplify this, we can, if we want to get velocity final by itself, we can do velocity final equals velocity initial squared plus 2a delta x. So there we go. Now we know. So I know I'm a bit messy, and I think it's because I'm nervous, but we now know how we get all our uniformly accelerated motion equations. So that makes sense, right? All we did was we took what already we knew, which is like acceleration and a graph of a not this always scenario, but a basic idea of it, a common scenario, and then we use that to use the variables to find the solutions to our problems, right? So that's basically it. So that's that. Next week, I'll try to explain a little bit more about the history of physics and the first steps, like how we figured out gravity was accelerating. How do we know that acceleration is always odd? It's always an interval, and why Newton, kind of annoying sometimes. We'll talk all about it. So for now, that's it, or just, I guess, me ranting. So I also have some problems for you guys. And we'll do a rotational kinematics question as well. But I want you to try this question. Hi, what's the difference between speed and average velocity? Right? Velocity is a vector, right? What does vector mean? Magnitude and direction, right? So what is speed? Speed is just distance over time. So if it says distance over time, I mean, I don't know that to show you. It'd be just 45 up, 45 down, divided by the 3 seconds up and 3 seconds down, which is just what, 15, right? See, easy enough. But it says average here. It says average velocity, right? Average velocity means velocity final minus velocity initial, and if it starts at 0 and ends at 0, because the direction matters, right? It'd just be what? 0 minus 0 over t, which is 6. So 0 over 6 is just 0. So it's just a. So it'd be C and A. So pretty simple enough. Just a concept question. So here's another one you can try. So we're driving 15 miles for 20 miles, 20 miles for 30. So it's just making you trying to understand that it's not traveling the full distance. So it travels in less than an hour for each and every. So if you do that math, or do it in your head maybe, it'd just be 20 over 15 plus 20 over 15 plus 30 over 20, right? Because that's how much distance I've traveled. Or 30 over 20, sorry. And then, what is that? 2.83 hours. So that's just time. And then what is velocity average? Delta x over delta t. And we know we traveled 35 miles, 15 plus 20, which is 35, over the 2.83 hours, which equals to 12.36, which is less than, obviously, 25 miles per hour. So simple enough. Here, there's another more concept question. Yeah, exactly, pretty much. Simple in the simple versions, exactly. I kind of want to show you the work that you can actually do, because conceptually it makes sense, but you can also do this in mathematical values, which I think is pretty cool, and I want to show you it. So, here, I'll show you that you can solve this with just formulas, right? So we know that. Yeah. So we know that the distance traveled for 1 second is greater than the second traveled total. So what does that mean? So if we say that s equals the distance, right? We can say that s t plus 1, because that 1 second, right? They're talking about. Oh, that's pretty small. So s t plus 1, right? Yeah, t plus 1 minus st has to be greater than st, right? Does that make sense? Kind of? Yeah? Okay. So this makes sense. It's just saying that this second, that specific second is greater than the second total. So this has to be true, because that's what we're trying to say, right? So what is what can we do with s? We know the distance formulas, right? So we can simplify this to gt plus half g, which is greater than half gt squared. Which is just what? Because it's in free fall, right? Simple enough, because you have to think about the interval t, and this is the t total. So if we simplify this more, we get rid of gravity. We get t plus half, which is greater than half t squared. Now we can simplify this again, so we can find what t equals, right? So half t squared minus t minus half is greater than 0. So what does that equal then? So we can simplify this again, because we don't need half, we can get rid of the half here. So t squared minus 2t minus 1 has to be less than 0, because we flip the signs and all that. Then we know that t minus 1 squared minus 2 is less than 0. So that makes sense. So now we can solve for t, right? It's pretty, self-explanatory. So t is less than 1 plus square root 2. So for our answer B to be true for short intervals, this has to be true, right? But what does it mean for past this value? If t is greater than 1 plus square root 2, then this doesn't become true, right? This becomes false. So that means it only works for short intervals between 1 plus square root 2. So that's why it only works for short intervals mathematically, which I think is pretty cool. I think it's pretty cool to see it be able to solve with values as well, beyond your brain. Here we go. Here's another one, pretty simple. Acceleration in the y direction is always negative 9.81 meters per second squared, which is always less than 0, or at least when you're on Earth, at least. I don't really know what's on Mars. I don't really know. Let's try this one. This is also another conceptual question. It's pretty similar to the previous one, but I do want you to think about it. Yeah, pretty much, just D. I mean, the kid's pretty stupid. I don't know why he's tossing a ball while he's jumping, but he's throwing the ball, but the ball, it doesn't matter if he's flipping, looping, turning, twisting, dancing, doesn't matter. He's still, when he throws the ball up, it's always going to be in experiencing gravity. So acceleration in the y would always be negative 9.4. It's simple enough. So try this one. It's the same thing again, but so what do you think? Yeah, it's B. It's just exactly negative 9. So here's a more conceptual question. This is just your values. So the minute hand of a wall clock. So just try it. It's not too hard. It's not too easy either. I think it's pretty unique, so I included it here. An equation?
Yeah.
No, it's just placement. Like when you think of a coordinate system, what is I? I is x. This is I. Imagine this is I, and this is J, right? What is I here? If this, okay. Negative 11.3. Yeah, exactly. Let me make this a little more visible. So, it's a clock. Makes sense. Big clock, big circle. We have a center, and it starts here, 11.3. Now it goes here. Now stop thinking about it as a clock, and instead think of it as an axis, or sorry, an axis, a graph, right? So if this is the initial 0, 0, or 0i, j, what is here? If we're thinking about I and j, what do you think? What's the coordinate?
0, 11.3, or 0, negative 11.3.
0 what?
Negative 11.3.
0, negative 11.3? That doesn't really make sense. That means it's just negative 11.3.
0, comma, negative.
Yeah,
0 comma?
Or I guess you could do I
Right,
and
Are you
J
asking for a
form.
coordinate?
But it's looking for a displacement vector.
Then it would just be
So it's asking for
negative
0,
11.3, comma,
I
yeah.
minus 11.3.
Yes, same thing.
Which is just, it's just pretty much the same thing. But they say vector, so that's why you need I and J. So that's here, right? But ignore the question. We can talk about that later. We want the coordinate here now. So what is that coordinate?
11.
Negative 11.3 I hat minus 0 j hat.
Yeah.
Oh, the phone. Negative 11 point. Yeah. 15 minutes past. Yeah, that's 11 point. Yeah. Okay. Pretty much.
What happened to Musa? He left? He's up there?
Yeah.
So, what is this? So we know it's negative 11.3i plus 0j, right? That makes sense. Or j hat. If we're looking for, what does the question say? The displacement vector of its quarter after 2
Just
half
add
pass.
them.
So we're just gonna look at 2. I don't want to talk about it again. So we're just talking about what happens here. So if we add these together, or subtract these together, we get what? We end up here, so it's like y2 minus y1 kind of. So it'd be, I need to make this look a little bit better. So we're looking for its displacement vector of this interval. So what do we know? It's y2, so that's where it ends up. So negative 11.3i plus 0j minus 0i minus 11.3j, right? So that should be pretty simple, right? It's just negative 11.3i plus 11.3j. Right? That's basically it for A. When I first did this, so if we remove time, right? What is A? A is like the time traveled, right? It's asking how much time is traveled, how long it took the trip. So what is B? B is the chain difference, right? So if we want to find travel, we first have to find its difference. So let's first talk about its difference. So in its time zone, 6 o'clock minus its time difference equals what is it? 6 o'clock. Oh, sorry, no, 5 o'clock plus its time difference. Does that make sense? Okay, I'm gonna assume that it makes sense. So, what is this?
I get a square.
All right. So 2AT equals what? Negative 11 hours. So what is delta T? So delta T equals negative 5.5 hours, which you guys got right.
Wait, hold on.
Have
What's
a good
the
day,
A?
Jackson.
What's
What?
the A?
A? There is no A.
Oh wait, sorry. I thought you wrote an A, not delta.
That's delta T. That's delta T. That's also delta T. So 6 o'clock minus the time difference equals 17 o'clock. Or sorry, not 7 o'clock. 5 o'clock plus its time difference. So if we want to, if the time difference remains the same, Los Angeles or whatever the other one was. So plugging that in, we know that 2AT equals what? Negative 11 hours, and delta T equals negative 5 hours. That makes sense, right? Not too insane. Yeah. Okay. So we found B. We found the distance. So what is the time travel? Well, we're looking for whatever it was. It was like time travel for the distance. So it'd be 6 o'clock minus negative 5.5 hours. So that equal to 11.5 hours. So that's it. It's pretty simple when you write it down, or like have a if you have the formula down, I feel like it gets a lot easier. So that's it. I'll just do C really quick, and then I'll just let you guys go. I want to play one video, but it's just a minute long video. I just want to show you that before you go. So delta x equals vt, velocity equals 520 miles per hour, and delta x equals what? 520 times 11.5. 11.5 is from the 11:30 hours. The 520 is given, like, right? So that equals to 5,980 miles. Theta is what? 360 over 24 times 5.5. 5.5 is from here. 360 over 24 is the 24 hours revolution. So that's time, which equals to 83 degrees west of LA. So simple enough, that part. And I looked into this and see what 83 degrees west of Los Angeles is. You can take a picture of this. It actually goes to North Atlanta or Brazil, which pretty crazy. It's just 83 degrees. It's a pretty cool difference you can make. So that's that. I thought we could do more questions, but it's fine. But I want to show you this one quick video, which will help us with the next thing I want to talk about next week.